Hello, everyone. The title of my video today is Do You Really Know What Ordered Pairs Are? And actually, this video continues the series on logic. Right? We're doing a series, as I said, every week I'm posting videos uh, promoting logic, promoting mathematical logic, mathematical rigor. This is the only channel that is really doing that. There are others who pay lip service to it, but really, this is the only channel that is taking it very seriously. But I wanted to ask you that question because I'm going to quote to you, I'm going to quote you a text from one of the worst mathematics textbooks ever written. And I mentioned it in my previous video, but the more I read it over and over, certain things, the it almost it makes my blood boil. The title of the book that I was referring to, in case you didn't watch the previous video, is this one, Pre-Calculus with Limits, which I happened to come across in a discarded, and rightfully so, by the way, a discarded book section in a library years ago. But I used to collect math books. I have a lot. And it's by Larson Hostetler Edwards. Now, this is the second edition. It's from 1997. 1997. And it says here, a graphing approach. I'm going to quote to you an exact quote on how they justify, how they describe what an ordered pair is. It says, first, this is on page 2, by the way. This is supposed to be a prerequisite for pre-calc. The Cartesian plane is formed by using two real lines intersecting at right angles. And then they show you a figure of that. The horizontal real line is usually called the x-axis. Usually called. And the vertical real line is usually, again that word, adverb, usually called the y-axis. The point of intersection of these two axes is the origin. And the two axes divide the plane into 4 parts called quadrants. And then they show, even though they don't describe it textually, but they show that it goes in a counterclockwise direction. And then it says, each point in the plane corresponds to an ordered pair, x, y, of real numbers, x and y, called coordinates of the point. The x-coordinate represents the directed distance from the y-axis to the point, and the y-coordinate represents the directed distance from the x-axis to the point, as shown in figure P2. Now, what a delightful specimen of modern mathematical exposition, if you can even call it an exposition. Diluted, pedestrian, and marinated in the lukewarm broth of uninspiring prose. Now let's look again at this passage as with an unflinching eye and see if it stands to scrutiny. First, we are told that and I'm quoting, the Cartesian plane is formed by using two real lines intersecting at right angles. Is it? Formed by using. What manner of slapdash waving is this? Hand waving, I should say. The Cartesian plane goes back a long time. It's not some crude construction assembled from spare lines like a barn raised by careless laborers. It is a set r to the 2 r squared, rigorously defined in the real numbers, and it exists in all its infinite and glorious totality before any arbitrary labels are slapped upon it. The so-called real lines, an odd term, why not say real number lines, or better yet, coordinate axes? They do not form the plane, they serve merely to organize our understanding of it. It's a subtle, yes, but crucial distinction, and the neglect of which suggests it's a lack of mathematical maturity. Next, we are informed that the horizontal line is usually called, right, the x-axis and the vertical line usually. What is this timid equivocation? Well, in the classical lexicon of mathematics, the x-coordinate was properly called the abscissa. How many of you know that term from school? Do they say the x-axis or do they say the abscissa? And the y-coordinate used to be called the ordinate. And those terms, in many cases, have been tragically abandoned by modern pedagogues in their reckless pursuit of so-called simplicity, which means dumbing down, by the way. It's a euphemism, and it's a euphemism for the gradual erosion of mathematical precision in favor of pandering to the mathematically faint-hearted. It is of no use to students who are serious. And one does not simply suggest their nomenclature as though if it were a matter of personal taste. It's like choosing between coffee and tea. And finally, we are given this. Each point in the plane corresponds to an ordered pair. Well, it's okay, it's a true statement, but it lacks elegance because the Cartesian plane, as we said, is a set of all ordered pairs r to the second. It's not merely a happy coincidence that each point corresponds to an ordered pair. It is an ordered pair. And that statement should be made with firmness, with the firmness of a mathematical axiom, and not the hesitant tone of a half-formed observation. Now let's turn again to the other part. He says, or the authors say, there are three authors, it's Larson, Hostetler, and Edwards. They talk about the directed distance. Well, what is that? It's a term that's tossed to us with no formal clarification, as though its meaning were as self-evident as the rising of the sun. Why not simply define the coordinates precisely in terms of projection functions? Why not state explicitly that the Cartesian coordinate system is an orthogonal basis for the Euclidean plane? Why indeed must we endure this? It really is a parade of imprecise explanations masquerading as simplicity. And this is another casualty of modern mathematical pedagogy. It seeks to describe where it should define, to suggest where it should assert. It's really mathematics drained of rigor. It's dressed in the finery of casual language and passed off as instruction. We need to discard this kind of prose. We need to be exasperated at this nonsense. And we need to return to rigor. That is why I'm doing this video. I'm doing this because we need to really understand what it is. We need to talk properly. I would never allow such a text in my lecture hall. Nay, not even as a footnote. I ask all of you watching this video, if you have a textbook, because I know nowadays you don't even have a textbook in some cases. What does your textbook look up in the index, ordered pairs, and tell me what it says? How does your textbook define ordered pairs? And you will be able to know instantly if you have a good textbook or not. So let's get right to it then. All right, I want you to start looking at, or reading rather, the notes that I put here on the board. Because we have thus far spoken of sets. We said that when you're dealing with sets, with the braces, the order is of no concern. So the set AB is really rather flexible. You can write it as BA. Such is the beauty of in that context, it can be very egalitarian, we'll say. Elements are admitted in whatever particular order, they don't have a particular hierarchy. It's much like the idyllic version of a republic, although one suspects that too much of such unordered liberty leads to nothing but confusion and anarchy. But there are times when order is not merely a convenience, but a matter of utmost necessity. And here the mathematical structure demands discipline, not chaos. So if you consider the coordinates of a point in the Cartesian plane, x and y, here you have the first element is first, the second is second, and you cannot interchange them in that sense. So the ordered pair 1, 3 is a wholly distinct entity from the point 3, 1. It's really rather much like a learned gentleman is distinct from a common ragamuffin, no matter how similar you think they might be in their soul. But appearance-wise, it does make a difference. So when we wish to impose such an order upon our elements, we have to abandon the laxity, and we no longer use braces in this case. We have to use the parentheses typically. So A stands as the first element, and B assumes the proper place as the second. And I put a little footnote here, the cross symbol, because you notice that the parentheses is also the symbol for an open interval. So, but in this context, we're not talking about open intervals. So we also have ordered pairs that are governed by a simple but inviolable law. AB, the ordered pair AB, is equal to CD if and only if A is equal to C and B is equal to D. Now, I must issue a word of caution. Because some of you are inclined toward idle speculation. What is an ordered pair in the first place? That was the question in the beginning of this video. Now, you might assume that such a matter is best left to the instincts of common sense, perhaps, or you say, I know what it is, I know it when I see it. But alas, in mathematics, nothing is accepted on the basis of mere intuition alone. We shall therefore have to furnish you with a rigorous definition, and I will do that in due course. But let no man delude himself into thinking that such a definition will enhance his understanding in any profound way, at least not yet. It serves merely to demonstrate that the noble edifice of mathematics, we have to rest upon a firm logical foundation and not the whimsy of intuition. So we proceed, we use reason as our guide, order as our principle, and mathematics as the unshakable fortress against the tides of disorderly thought. What is an ordered pair? How should it be defined? Well, in the first place, let's have a look at the following definition. All right, now you should be able to see the definition on the board. The ordered pair, what it is. This is an essential construct in our mathematical arsenal. It really looks like a thing so deceptively simple, and yet it's so vital to the very foundations of analytic geometry and beyond. So any misstep in its definition would cast our entire logical edifice into ruin. Now, if you're one of those people who fancy mathematics a mere practical convenience, rather than it being the mutable law governing rational thought, would do well to sharpen your wits here, because we're not going to proceed with pleasantries, but with proof. So let's look at the definition. The ordered pair AB is none other than the set whose members are, elements are A and AB. And if we write it in unassailable symbolic form, you have what you see on the board. Now notice, ladies and gentlemen, that this construction is not an arbitrary decree. It is a necessary formulation. One that if we are going to accept it, it must indeed exhibit the defining property of an ordered pair. And that is our theorem comes into play. And we're going to prove this theorem by the method of irrefutable deduction. First, see if I can show you the proof here, because everything is not coming in. There we go. Hopefully you can see more. There's a lot to say here. But you're going to suppose first that A equals C and B is equal to D. Well, we have our definition here. So one direction of our biconditional statement is immediately secured. Now for the converse. If AB is equal to CD, we assume that, then by definition we have A and AB is equal to C or CD and CD. So our task here is to extract from this equality the inevitable conclusion that A is equal to C and B is equal to D, and we really can proceed by distinguishing two cases here. So in the first case, the set AB collapses simply to A, and it reduces our definition to AB is equal to A. Right? Hopefully you can see, I know the print is rather small, but I just wanted you to see this. Right? And so if we equate both sides, we can deduce that A is equal to C, CD. But the problem is the left hand set, you have a single element. It possesses a single element, meaning that the right hand must also have but a single element. And thus we conclude that C equals CD. And from this, C is equal to D. And furthermore, since A is equal to C, we obtain A equals C. So A is equal to B, which is equal to C, which is equal to D. And our proof is rather very much completed here as required. But then we have symmetries here. You got to think of symmetries of definition, right? If C does not equal D, well, remember our assumption is AB equals CD. So it has to be that A belongs, it's in the right-hand set, meaning that A equals C. It corresponds to C. Or A equals C and D. Of course, the latter is impossible, right? Because A has a single element, and C and D contain two elements. So we have to deduce that A is equal to C in that case. But have a look and let me know, where is it here? I've used the set notation that we were discussing before in the previous videos. So do not dare to challenge the precision of formal mathematics. We have a proof here. We have a definition here. Some people they wander blindfolded through the corridors of mathematics halls, rather like indolence on the streets after they have an excess of spirits. But if you've grasped this concept, we are going towards higher reasoning, because the next definition, or rather, we're going to deduce some principles as well. All right, the final topic for this video is going to be the Cartesian product. You really need to understand here the context, which is the algebra of vectors, because when you're dealing with physical quantities, when you're dealing with temperature, length, time, and mass, you can really represent that as a single real number on a linear scale. And those are called scalar quantities, by the way. But when you start dealing with in more advanced concepts like velocity, acceleration, force, or any kind of displacement, really, you require two or more. You need two or more members for the expression, and those are called formally vector quantities. And you need ordered pairs in order for you to do that. Ordered pairs and points. So there's something called the Cartesian products, and I'm giving you the definition here on the board. It looks like A times B, but really you should read it as A cross B. And A cross B is XY, as long as X has to be an element of A, and Y has to be an element of B. So for your particular level, the Cartesian product you should be most interested in at the high school level or beginner level, at least in college, is the set of the cross product of the real numbers, R cross R. And we say that two ordered pairs, X and Y and AB, are equal if and only if, which is really, if ever you see if and only if, it's really two rules. X equals A and Y is equal to B. So as an example that I'm showing you here, you determine the set of real numbers of X for which X squared minus 2X and X plus 3 equals 0,5. Well, we solve each one separately. Your X squared minus 2X, set it equal to that 0, corresponds to that 0. We factor out the X and we get 0. X equals 0, or X is equal to 2. But notice what happens in the second case. X plus 3 equals 5. That means X has to be equal to 2. So the only solution here, in fact, is 2. And you will find that it holds true for both. If you plug in 2 back into the expressions, it gives you that ordered pair. The other example would be this. Give a roster of S equals this, X minus 2Y, X minus Y equals 3, 4. Well, we solve it. We're going to have a system of equations here. If we solve the system of equations, we get X equals 5 and Y equals 1. And therefore, if you plug it back in, you get equal to 3, 4, the ordered pair. So the roster, the list of elements is 5 and 1. Now you notice that all of the, I hope that you've noticed by now, that the ordered pairs follow the properties, the symmetric property, the transitive property as well. And really, if you look at it as an exercise, for example, so you have the principles here. You have reflexive, symmetric, and transitive. And here are some examples that you can look at. But what about these three questions? Which of the three properties apply to each of the following relations? I want you to take a look at it. Pause the video, let me know. Did you pause the video? Well, for the first one, you should have symmetric only. For the second one, you should have transitive only. And for the third one, actually, all three apply. Next week, when we continue the logic series, we will talk about functions. So hopefully this was useful to you. Please subscribe to the channel if it was. I appreciate all of your support. And if I don't answer some of your comments, I cannot keep up anymore. I feel so blessed to be in the presence of such wonderful young people and not so young, doesn't matter. But I do feel very, very blessed. You are really the reason. You are the highlight of my days on YouTube when I do this, because I really enjoy your feedback. I enjoy your comments. I enjoy the few times I can have some discussions. If you really have deeper questions, though, like if you want to have a theological debate with me, it's much easier to write me a letter. You have my mailing address, and if you don't have it, I'm posting it here in the description. All right, everyone, may you have a blessed day. Hopefully, you're warm wherever you are. It's been another rough few days here in Lynchburg. Here in Lynchburg, it's been snowing. It's been a really horrific winter, although I shouldn't say that. I should always thank God. It's a bad attitude to have. And I should always thank God that I'm still alive and that He blesses me with all the things that I have. So thank you all and enjoy as much as you can anything you have, and thank God for that.